Hello everyone, and welcome to today's math lesson with Everyday Seminar. Before we begin with today's topic, let's go through the solution to last week's question. Now, say for example, I flip a coin 9 times and each time I get a heads. What would be your guess on the 10th flip? So I flip a coin, 1st, 2nd, 3rd, 4th, 5th, all the way to 9th. I get heads all the way. So on the 10th, what's your guess? Tails or heads? Well, the most people who would follow the gambler's fallacy would think that since there are so many heads, the next one will be tails. Okay? Which is wrong. It won't be tails. And in fact, the correct answer is 50% and 50% heads or tails. So either one. The probability is 0.5 or a half each. Now, the gambler's fallacy, it's a term meaning that people look at the events before one event, and they think since there are so many heads, this one for sure has to be a tails, since there are a lot of heads. But the problem is, the 10th flip of a coin is an independent event. Okay? The 10th flip of the coin does not depend on any of these before it. In relation to this, there's also something called the law of large numbers, right here. And what this shows that every time, say for example, that's tails or heads. Now, if you toss a coin for a very long time, eventually the ratio will find its way, it'll become closer to 50 and 50%. You see that graph there? Okay, that's the law of large numbers. And, okay, so the answer, 50% heads, and it also has a 50% chance to be tails. Let's move on. Hello everyone. Okay, so today's topic is we're going back to do some revision on Venn diagrams before we do more on probability theory. So here it's just, we're going to cover just a brief introduction on Venn diagrams. Key terms for today: Venn diagram, notation, and a probability tree. Okay, and here's a nice little diagram I got off the internet. Let's move on. Okay, Venn diagrams and probability theory. As we move on with our probability theory episodes, we need to have a brief understanding on how to read Venn diagrams and the notations for Venn diagrams. This will also be important in reading information from probability trees. Okay, here's an example. And we have some of the notations here also used in Venn diagram, these kinds of signs. Okay, let's move on. What is a Venn diagram? A Venn diagram is a diagram that uses circles to illustrate the relationships among sets. So that's set A, B, and C. Venn diagrams were invented by a guy named John Venn, we have the Venn here, as a way of picturing relationships between different groups of things. Since the mathematical term for a group of things is a set, okay, that's a word we're going to be using often, Venn diagrams can be used to illustrate both set relationships and logical relationships. So what does this mean? I'll show you in a sec. Okay, so here we have an example of a Venn diagram. Okay, quadrilaterals is the main set we have here. Now, under quadrilaterals, we have things called trapezoids or trapeziums, parallelograms, rhombuses, squares, and rectangles. Notice that quadrilaterals are on the outside and parallelograms are inside the quadrilateral box. Okay, but parallelograms have no relationship here to trapezoids. That has its own circle, and the circle is not touching the parallelogram circle. Now, under parallelograms, the types of parallelograms we have rhombuses, squares, and rectangles. And squares is a combination of both rectangles and rhombuses. Okay, first of all, I noticed there's all of these basically we're mostly familiar with squares, but there's a slight difference in trapezoid, a parallelogram, or rhombus. This, for example, basically all 4 equal sides with 2 parallel lines. Rectangles basically 2 sides of equal length. Parallelogram is just a stretched out rectangle. Okay, parallel lines there. These 2 lines are equal. And a trapezoid has one set of parallel lines and so forth. Quadrilateral basically means any four-sided shape. Okay, let's go through another example. So, here another way, instead of a Venn diagram, we can use a tree diagram to show relationships. Okay, a tree diagram like that above can be used also to show relationships like a probability tree. Venn diagrams enable us to look at the same information in a different way. So what is a set? A set is a collection of objects called elements. So the set of living things, we have these elements: bacteria, plants, and animals. And animals have its own set, and underneath it, mammals, reptiles, fish. Mammals includes whales, humans, horses, and here are some examples of some famous humans in Japan. Let's move on. Okay, so here we have a very good example. This is a tree diagram, and we're going to show this using a Venn diagram shortly. So these are the sets of numbers. Okay, this might be important to some of you. Reals or real numbers, they have two branches, two sets: irrational numbers and rational numbers. Those are examples. Now, rational numbers can further be broken down into subsets or elements of the fractions or decimals and integers. The examples. Now, integers can be further broken down into whole numbers and negative integers, and whole numbers can be broken down further into natural numbers and zero. The question is zero a number? Think about it. Now, what we've done here, we've used a Venn diagram to display the following sets of numbers. So we had the sets: real numbers, rational numbers, irrational numbers, integers, whole numbers, and natural numbers. So these are all under real numbers. Notice that imaginary numbers, the circle here is outside of the real numbers. So the types of real numbers we have rationals and irrational. Okay, now the types of rational numbers we have inside, we have integers, and the types of integers inside that circle, we have whole numbers, and the types of whole numbers inside natural numbers. Okay, let's move on. Now, here's an example. Let's say that our universe contains the numbers 1, 2, 3, and 4. Let A be the set containing the numbers 1 and 2. So this circle will be A. Let B be the set containing the numbers 2 and 3. That would be B. Or that would be. Then we have the following relationships with pinkish shading marking the solution regions in the Venn diagrams. The Venn diagram is coming up. But firstly, let me show you here. We can even have a set C. So that can be A, that one. A has 1 and 2. B, the set B has 2 and 3. And we can even call this C. So C has 4 in it. And inside set C4, we have A and B. They are inside C. Now let's have a look at here we are, solution sets. Okay, so first of all, we have A union B. Okay, union. And this means everything that is in either of the sets. So everything inside A plus everything inside B. That's why we've circled both circles of A and B. So the answer to A union B is 1, 2, and 3. Another important one we have there is this, intersect. So A intersect B, only the things that are in both of the sets A and B. So there's only one number in A and B, and that's 2. 2 is in A, and 2 is also in B. So we've highlighted that central region, pink, the answer 2. The next one we have, let's read here, A complement, which means everything outside of A. So that's why that A circle is not highlighted. So what we have are the numbers 3 and 4, everything outside of A. The next one, we have A minus B, or A complement B, everything in A except for anything in its overlap with B. So we just take A, it's basically A, minus everything in B, so we rub out B, and then the answer is 1. Oh, yeah. Next one, we have not A union B. So that means not included. So everything outside A and B, everything away from the union A, union B, which equals to C, who we labeled before, which equals to 4. And finally, we have everything that is not, okay, not within the intersection or A intersect B. Everything outside of the overlap of A and B. Everything outside this overlap between A and B. So we highlight pink. Everything outside, the answers 1, 3, and 4. Now the main ones I really want you to remember is this union, which means basically addition, plus an intersect. Intersect and union. Union, which means one, okay, or all, and this intersection where they join. So A intersection where A and B meet, where they join, and A union B, all of A plus all of B. Okay? Now, here's our homework. On our same example that we just did, highlight the solution set for A union B union C minus A intersect B. Okay? Remember, that's A, that's B, and outside, just outside these circles, inside the box, is C. So what would be the solution set if we were to highlight the solution set for A union B union C minus A intersect B? Okay, and thank you very much for viewing today's lesson. Hope you had a good time. See you next time.